Hi, I'm Craig Rowland, founder of Sandfly Security. Today I'm going to talk to you about evasive Linux backdoors. This is a presentation I gave at the Cold Incident Response Conference recently in Oslo, Norway. Now, visiting Norway is really fun. I wanted to troll them with this meme, but I was so jet lagged, I actually did something one up. I referred to Norwegians as Swedes, thanking them for having me out in Sweden. And I learned actually this is a bigger insult than this meme itself. But anyway, I wanted to get into this very quickly. And the thing is, my talk is about evasive malware and how it operates on Linux. Now, evasive malware is a little bit different from what a lot of people think about in terms of malware. A lot of people, when they think evasive, they think stealth malware, but that's not actually what my definition of that is. Evasive malware is using simple tactics to avoid detection. It's not going to great lengths to avoid deliberate people trying to find it. And that's kind of the difference here. Evasive malware is hiding. It's using simple, widely compatible tactics that aren't going to cause any system stability problems. Stealth malware, on the other hand, is what a lot of people think about in terms of Linux malware and rootkits. Stealth malware is far more complicated. It's typically hooking into the kernel. It might be using kernel hooks or eBPF to hide. And this sounds really cool, but in my experience, it causes a lot of problems. It causes performance impacts, it causes system stability impacts, and some other problems. It also doesn't work across a lot of different kernel versions, so it makes wide deployment very, very difficult. And this to me is really the primary differentiator. Evasive malware is doing enough to hide from accidental discovery. Stealth malware is trying to hide from deliberate discovery, and these are two very different things. Evasive malware can remain present for a long time because it's not trying to do anything tricky to hide itself. Stealth malware could cause trouble on a system that actually gets people to start looking for it, and that actually can make it get found a little bit easier. So what's interesting about this is that a lot of people think stealth malware is a bigger threat than evasive malware, but for me, it's actually the opposite. I actually feel evasive malware is a bigger threat than stealth malware. Stealth rootkits never really bother me. Malware that's just simply trying to be evasive and widely compatible, that's actually the real problem. Now, this whole story starts at midnight. I'm holding a screaming child, trying to get it to go to sleep. And sometimes when you're dealing with a screaming child and you just want to hang out with other screaming children, there's only one place for you to go. And that place is Twitter. And in particular, I'm doom scrolling InfoSec Twitter, trying to get this crying child to go to bed and see what everyone else is crying about that day. And someone posted a really interesting link. And this is actually it. They put down some source code on this pastebin link that you see here in the slide. And they said this was a backdoor used by the red mentioned Chinese state actor group. Now, I don't know who wrote it. This is just what they wrote down here. But the whole point is I looked at this malware and I knew immediately that I was dealing with something very unique and special. And I'm a bit of a connoisseur when it comes to Linux malware. That's all our company does. My company, Sandfly Security, we do agentless intrusion detection for Linux. We see heaps of malware, heaps of rootkits, heaps of attack tactics all the time. But this malware in particular immediately passed what I call my malware leet heuristic. And basically what this is the more greets and ASCII art and leet speak a piece of malware has in it, the less seriously I take it, the more I consider it amateur. Where malware that just kind of gets to the task at hand and doesn't make a big fanfare of things, that's actually the most successful and professional malware I tend to run across in my career. So when I saw this malware, the fact that it just had one very focused task and it did it very, very well without a lot of fanfare, it immediately got my attention. Now, you can kind of see it here in BPFDoor ran. When you run BPFDoor, it just comes back with a command line in a split second. But in that split second, it did a lot of things behind the scenes that really indicated to me it was written by people who knew what they were doing. In particular, it had a combination of elements that really got my attention. First of all, it used masquerading of the process name. It deployed anti-forensics in a very intelligent and useful way. It had a very clever security bypass that was built into it that actually leveraged firewall rules against the firewall itself in order to work. And it uses encrypted communications to protect itself, along with a covert channel communication to activate. So I run into Linux malware all the time. As I said, you might find one or two things in a piece of malware, but it's very unusual to get all four of them packaged together in one place. That's why the fifth point is here, professional. I feel that the packaging of this malware with all these elements working together in a very cohesive way made it a professional piece of malware that needed to be looked into. So masquerading. The first thing this malware did when it started is it wanted to protect itself against accidental discovery by trying to pretend to be something that it isn't. That's what masquerading is. Masquerading is essentially just trying to pretend to be something that it isn't. This case here, it's a viper wearing some sunglasses, trying to say, hey, don't look at me. And that's essentially what BPFDoor is. BPFDoor is a viper. And for masquerading, it picked a random name that you see here in this list. It doesn't really matter what these names are because there's lots of variants of there out there now, and it's going to change. But the main thing is whenever you ran it, it picked a new different name to hide under to make itself harder to find. With the execution in our example that we're using in the slide deck today, when I ran it, it picked the udevd daemon. This is basically a device management daemon on Linux. And a couple interesting things here. First of all, the process ID we'll use today for a demonstration is 3306. That's what it's running as. udevd is the name of the process here. It is not using a lot of memory. And also, this malware got its name BPFDoor because it's using Berkeley packet filter in order to do packet sniffing. And that filter gave it a very high efficiency from sniffing packets, and it didn't allow it to use a lot of CPU time. So again, for an evasive piece of malware, it's using a masquerading name, it's not using a lot of memory, and it's not using a lot of CPU. If you saw this process in this process listing, you wouldn't really think anything of it. And again, you compare that against the stealth malware. Stealth malware would actually go out of its way to try to hide itself. This malware is not hiding the process name at all. It's just giving itself a process name that you would completely expect to see, and it's not doing anything unusual other than the fact that it's just sitting there. You would have a very tough time finding this accidentally. Now, in order to find a process that's masquerading under Linux, we're going to use basically 4 main commands. The first one is one I really like. It's just a PS command with the AWX WWF flag. This gives a process listing with a parent-child relationship tree so you can see what parents spawn what children underneath it. The PS tree command does something similar, but it's not always loaded in every host. Then the next thing we're going to use is we're going to use the ls command on the proc directory, and then a simple strings command to see if the command and the command lines actually match. First of all, we're going to go to the proc directory. What I mean by that is cd/proc, and then we're going to go to the process ID, which again is 3306 for today's demonstration. And we're going to do just a simple ls command. The ls command is going to show us a whole bunch of different files, but the most interesting one we want to look at first is what is the name that the exe points to. The exe is essentially the binary that kicked off that process, kind of like an exe under Windows, but here it's a Linux binary. But the point is we immediately get our first clue that there's something very, very wrong with this process. And that clue is that it's pointing to a link showing dev.shm kdm temp flush with a deleted. For those of you who don't know, the dev.shm directory on Linux means shared memory, also known as a RAM disk. What this means is any file written to that area is only going to be in RAM, which means if the system reboots for any reason, anything in that RAM disk is going to be instantly destroyed. This is why it's a perfect location for a malware to be in, because malware doesn't like to be seen and caught or hanging around. And if it writes itself somewhere on the disk where it has persistence, when the system reboots, the binary may still be there and allow it to get caught. Here, by copying itself into the RAM disk, it immediately gets a volatile area to operate from that if something were to go wrong, it's not going to have a binary hanging out. The second thing is we see it's got that weird name, kdm/tmp flush, and Linux very nicely puts the word deleted in parentheses after it. That's actually put in there by the kernel. And what that's telling you is that that binary that started this process, it is no longer on the disk. So this process is running, but the binary that started it is no longer present, which in and of itself is suspicious. That tells us that someone's trying to cover something up. Now, going one further, how do we tell the true masquerading nature of what's going on? Well, first of all, the exe links is dev.shm kdem flush, and we're going to look at the com and the command line portions of the proc file system. If we do a simple strings command on com, that's going to be the command name that we see when you do a PS listing. This is what PS is actually reporting on when it says, hey, this process is running. This is the name it has. Command line is going to usually be the process name and any command line arguments that were fed to that process. So this might be a little bit longer. But here, in the case of our masquerading process, we already see something really odd. Again, the exe, the the COM and the command line, generally speaking, there should be some semblance of a match, right? So if you're running a web server like an Apache or Nginx, it'll usually be the executable would be called Nginx, and then the COM will have Nginx, the command line will be Nginx with all the commands in it. Not always. There are some commands that if you start them under a different name, they do something else. But most of the time on Linux, there should be some semblance of something matching between all three of these. In this case here, that's not. And what makes us even more suspicious is that, again, it's running from a RAM disk and it's deleted itself. And that does not match the COM and the command line. So we already know that this is going to be a problem. The next thing this did after it did process masquerading is it deployed a variety of anti-forensics. And this is where I'm going to back up a bit, explain a little bit more about my background so I can explain why the anti-forensic side is very important. I got my start working on the red team. Specifically, I wrote network attack tools, network attack libraries that are part of a vulnerability scanner. So the vulnerability scanner would then be used by consultants to do red team assessments of various customer sites. So I was developing the tools that other people were being used to deploy into the networks. Now, the reason why this is important is because there's a difference between the designer of an attack tool and the people who are operating it. As a designer of the attack tool, my job is not just to get the attack to work, but also to operationalize that attack in a way that it protects the people who are using it, right? So I've never worked for a government or a government intelligence agency, but if I did, I would suspect they would have inside those organizations tool development and then the field operators, right? And these are going to be two different teams, and these teams are not necessarily going to know what each other are doing for security reasons. The people designing the tools are going to be said, we need this X, Y, and Z. They're going to design X, Y, and Z, and then the field people are going to take it out and use it. But the designer of those tools are going to want to protect the operations guys against being caught. And that's what I think we're seeing here with a lot of the anti-forensics that BPFDoor was using. Now, to kind of get into this a little bit deeper, first, we're going to notice that BPFDoor did three things in the anti-forensics world that, again, lead me to believe that this was probably done by people who really knew what they were doing. First of all, it did the binary deletion, which we touched on in a bit. I'll talk about that in a little bit more. It did an environment wipe, which is highly unusual for Linux malware. A lot of Linux malware does not embrace the environment. I'll talk to you why in a moment. And finally, did some time stomping to protect itself in case it failed to initialize properly, which again is another fail-safe mechanism, which leads me to believe this is done by people who knew what they were doing. Now, let me back up by saying, first of all, everything I'm about to show you only works if you don't kill the binary. And a lot of people, when they're dealing with an incident, they want to go in with guns blazing, pew, 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 and just start shooting things in the head. And if you kill the process, nothing I'm going to show you is going to work. So just please leave a suspicious process alone. If you're an admin and you don't know what's going on, call your security, call your incident response team, let them take care of things. Don't go killing things unless you know exactly why you need to be doing it. So in this case here, what do we have for the binary deletion? The binary deletion basically is it runs the binary, removes itself from the disk. Again, so in case the system reboots or there's some other problem, that you don't have a binary hanging out waiting to get discovered. Now, a lot of people think that this is a really effective way to hide that binary from getting discovered, but it's actually not. This is what it looks like, first of all. We looked at this briefly. You do LSAL on the exe on the proc file system. The proc file system says, hey, that exe links to this path, and oh, by the way, it's deleted. Always remember, Linux is the premier open source operating system in the world, which means open is the operative word. It's not trying to hide anything from you. Here it's telling you, hey, this binary has deleted itself, right? It's being helpful to you. And a lot of people say, well, it's deleted. Oh my God, I have to pull out the memory forensics. I got to pull out the file carving tools. I got to attach the debugger. I got to, dump the stack and do all this stuff. And really, it's none of that. It's very, very easy to recover a deleted binary that's running on Linux. And that is, we're just going to copy the exe. And we don't need to overcomplicate this. All this works, again, only if you don't kill the binary. And we're going to do this very simply. We're going to simply use a cp command on /proc, the process ID, exe, and then our new file name we want it to be under. We can even run the SHA-1 or SHA-256 or SHA-512 on that binary directly as well. And if you don't want to write the binary to the disk, like let's say you're worried about overwriting evidence that might be on the disk, which is a good idea, by the way, You can simply use the SCP command. You can SCP that binary over to a new system, so then you can have that binary there for the debugger and detonation, all these other things you might want to do. But the main thing is, again, only works if you don't kill the binary. If you kill the binary, all this stuff goes out the window. Here's some examples of what it happens. So here we're going to copy cp.exe to temp suspicious file. I can run a file command on it. Yep, it's an ELF 64-bit executable. I can do lsal. I can see it's a 39K file. Again, this BPFDoor was simple, focused, and highly efficient. It's not using up a lot of memory, right? So 39K, pretty small package. I can run a SHA-1 sum on. I can do anything to that file that you would any other file on Linux. It's a real file at this point. I've easily recovered it. Now, the next thing this binary did after it executed itself is it erased its environment. Now, let me show you an example of what I mean by environment. The environment on a process can be investigated very, very easily. And what this means is that when a process starts, it has all the environment variables that the shell had when it began. We can use the strings command on proc, the process ID environ, or the secondary command if you don't trust the strings command. And what I mean by don't trust is there is a very, very, very old bug in the strings command. It's probably a decade old at this point, where in theory, if all the stars aligned, someone could possibly insert malicious commands inside a file and get a strings library that's part of a library decoder to execute them. Again, if you're worried about that, you run the second command. I'd argue that if your strings command is a decade old, you have bigger things to worry about, but I leave it here for you to decide. But basically, we need to look at what the environment is. The environment variable has a lot of nulls in it. These two commands strip the nulls out, replace them with line feeds, and allows it basically for you to see what's going on. So when I logged into this system, this is what a normal process environment looks like. And if you've never done this on Linux before, I highly encourage you to go take a look. I logged into a shell and my shell process ID is 3233. I did strings, proc, 3233, environ, and it just shows you everything that's running in my process environment. And what a lot of people don't understand is a Linux process environment leaks a tremendous amount of information. In the case here, I started this shell. I came in over SSH. SSH very kindly lists out the SSH connection. It tells you where I came from and where I connected to. The SSH client information is down here. I've seen all sorts of things leaked. I've seen remote username information in here. You'll see proxy information in here. Other tools like Netcat and NCAT, SOCAT, proxies will leak IP information in here. So you'd be amazed what's left behind in a piece of malware that's running. Some malware will run and it will clean all of its IP addresses out of the logs very effectively, but the binary itself will continue to have the IP addresses of the SSH connection it came over when it brute forced itself onto the box, right? So this is the type of thing that people forget to do. Now, BPFDoor, what do we see? Nothing. You run an environment command, it's completely empty. This is very unusual. So you'll get like kernel threads and some other child processes may not have a process environment, right? That does happen. But for one started from a shell environment, that should have some type of environment variables with it. It might not have much, it should have something. This had absolutely nothing. So at this point, what do we have? We have a process that was started from RAM disk. We have a process that deleted its binary from the disk. We had a process that is masquerading its name. And finally, fourth, we have a process with no process environment associated with it at all. These four things, you should have your incident response plan underway right now, right? This is obviously, this thing is very malicious. So you should be in incident response time totally at this point. We know this process. I don't need to know anything else about what it's doing. I know just on those four things alone, this thing is highly, highly unfriendly. But here's the other thing. Again, remember you had the tool designer and the operator. So the tool designer is protecting the operator against getting found by having the tool execute. But once the backdoor started running, the tool designer also protected the operator to make sure that backdoor that they're running, that bind shell that they spun up, also wasn't leaking any information. So at that point, what we see here is we went to strings on the environment of the shell. So here I started the reverse shell. I started the bind shell up from BPFDoor. It started as process 3985. I did the environment strings environment on that. And here I see something different. First of all, his file is sent to dev null. Again, another anti-forensics technique. This basically means don't write any data to the history file. Two, MySQL hist file set the dev null. This tells us that the people behind this tool had a keen interest in MySQL database, and again, they wanted to make sure that the operators didn't leak any information. 3, the path. The path is very interesting. They set it to bin, and then they had the Kerberos bin and sbin commands paths right behind it. This tells us that the people operating this also had a keen interest in the Kerberos authentication system, and perhaps what that entails as well. So even though they cleaned up the environment to make it very minimalistic, the fact of what they left behind and why they left it there tells us a little bit about the operators, kind of what they're interested in terms of this type of tool. Now, the last thing the tool did after it initialized itself is it time stomped its binary before it deleted it. Now, what do I mean by that? I mean, in this case here, I got the binary to fail, and it left a timestamp of October 30th, 2008. Now, why did I leave a piece of birthday cake there? Well, because I don't know what the date means. I looked around. Did the date have some specific meaning? Is it a holiday in a particular country to give away where it might have come from? Maybe it was the guy's birthday that wrote the tool. I don't know what it is. But anyway, the point here is the time stomping, again, is a fail-safe mechanism. If for some reason this backdoor did not start, something caused it to stop execution halfway through and the binary got left behind by accident, the time stomping is a last-ditch fail-safe to keep it from getting easily found. And not just easily found, it also is a fail-safe mechanism that if an incident response team were to find it, it doesn't give them a good date to start bracketing when the intrusion actually happened. October 30th, 2008 is ages ago, right? So it doesn't give them a time to start bracketing it. And also, as an incident responder, sometimes you might run a find command that says, show me all the new binaries and files made over the past, like, I don't know, 24 hours, right? That's a useful thing to do. In this case, that find command would completely skip over this. You just wouldn't see this binary because it's outside a normal window you would be looking for. So again, a very simple and effective and evasive way in order to hide that the malware is present. And again, a fail-safe way to protect the operator of the tool that the designers of the tool left in there just in case things went sideways. Now, the meat and potatoes of BPFDoor is how it bypassed the security. In the case of BPFDoor, it actually had a very clever thing that it did. Now, first of all, let me talk about how not to bypass security, right? So a lot of Linux malware is very, very clumsy in terms of hiding, right? They shoot EDRs in the head, they disable firewalls, they uninstall antivirus products, they maybe nuke log files and try to hide. Very, very clumsy. A lot of stealthier malware might make the system unstable. And, you know, I'm not joking about that. I really do, and I really am serious. A lot of stealth rootkits make themselves known by causing the kernel to panic. I've seen it multiple times, or big system performance impacts. But the thing here is that you combine that with other operational aspects, such as weird network traffic going to a weird port or a weird protocol. And it's just like, yeah, a lot of this malware is kind of easy to be seen. Now, how not to be seen or how to hide? Again, from an evasive Linux malware point of view, you're going to want to do 3 things, basically, and BPFDoor does all of them. One, it disabled security controls only when needed and exactly what was needed to be done. It wasn't doing just blanket shooting everything. It was very specific in what it did. It was focused on low impact. So again, it did one task very, very well, and it did it in a way that wasn't going to cause anyone to go looking for it. That's the thing, right? You don't want people to get to say, why is the system acting odd? I better go take a close look. That's the last thing you want is evasive malware. And 3, it deployed covert communications and encrypted communications to protect itself. Now, when I was in Oslo, I got a tour of the Norwegian Resistance Museum that they had during World War II. About 1/4 of the displays were about covert communications and hidden radios and hidden transmitters. In this case, this is a bottle of lacquer, but inside it, they had a whole radio shoved inside. It was a very neat little thing. But the whole point here is that covert communications, protecting your communications is so important to ancient and modern warfare that even today you see it in cyber warfare tools. They're going to want to protect themselves. And BPFDoor did these things. And better malware, again, is also going to do these things. It's going to protect itself from being discovered by having its communications compromised. So how did BPFDoor work? Why did it make it so effective? It was effective because it used a very clever way in order to activate. BPFDoor got its name because it had BPF filters that would look for a magic packet. That magic packet would have a piece of data in it, and a correct command and a correct password. And when all those things matched, it would then execute. But here's the thing that made it work so well. A lot of people don't understand that on the firewall on Linux, if you're sniffing traffic, the sniffer sees the traffic at the same time the firewall does. So just because you're running a firewall doesn't mean you can't sniff traffic. In the case of BPFDoor, it's sniffing traffic. A packet would come into the firewall would block or drop or do whatever with that packet. It'd be like, hey, look, I worked. I'm a good firewall. I did the job I was supposed to do. But it didn't really work. The implant still sees the packet. If that packet has the correct magic data in it and that correct password, it's going to activate. And here's the secret of what it did, that what made it so effective. It would open up in the case of a bind shell. It also had a reverse shell capability. We're just talking about the bind shell today. It would open up a shell attached to a high port. Then it would instruct IP tables to redirect all the traffic from the origin system that sent the magic packet to that new port. And this is what really made it very clever, because you're running your IP tables thinking that it's protecting that box with a firewall. But here it's using the IP tables actually to route the malicious traffic to the port in a way that's not going to be found. A practical example, how does this work? Let's say on my example here, I have my legit port is port 443. It's a web server. My spy here, he sends through a packet with the magic data in it. The magic packet is seen by the implant. The implant says, I see that the magic data is present. I see that the password matches. I'm going to activate. How does it activate? One, it sets a shell up on a high port in the 40,000 range. Then two, it tells IP tables, if you see the next packet from this user, this IP address, don't send it to legit port. Instead, send it down here, redirect it to the shell port. So what this means is all traffic is still going to port 443, but instead of being sent to the server, it's being routed down back over to the shell. So if you're watching network traffic on this box externally, you're only seeing port 443 traffic. You're not seeing traffic going to a new shell port. But the attacker is sending all the data to that port. It's going down and getting routed into the shell and back out again to the attacker. And this is what makes this BPFDoor so dangerous, is that very evasive, very slick way of hiding on the box. Again, it's not doing anything really fancy. It's not rewriting packets at the kernel level or doing anything of the sort. It's using IP tables itself to do all the dirty work for it. And it's using that BPF filter as a way to keep packets from hitting the CPU, what we call the slow path. And by not having all the CPU time getting tied up by analyzing packets, the malware, again, doesn't attract any attention. If you look at this, even on a very, very heavily loaded box with a lot of network traffic, that implant is going to have basically zero CPU time being used and essentially no memory, because it's not processing any packets at all. They're all being bounced before they even get to it by the BPF filter that it installed. Right, so we have that working. Now, how do we find that a process is sniffing traffic? Sniffing traffic on Linux can be found. I'm going to give you 4 ways to do it. All 4 of these ways should show the same process. I've seen malware hide itself from 1 or 2 of these, but I've never seen one hide it from all 4 of these mechanisms, okay? First of all, we're going to use LSOF, then the SS command, the cat command, and the ls command. Notice, again, no debuggers, nothing really fancy. These are all very simple commands. First of all, LSOF-P with the process ID 3306. This is going to list out all of the open elements that this process has. In this case here, process 3306, we see again that ktemp flush, again, that weird name. We know that's suspicious already. Here, the type of socket it has open here is going to be a packet type, pack right here. And again, the type is sock raw. What that means is that it's grabbing all network traffic. A raw socket is grabbing all the traffic it's seen coming to the host. We know this thing is definitely grabbing traffic. Now, I've seen some malware hide itself from this, so you wouldn't see anything here. So what's another mechanism we can use? Another mechanism is we're going to go to the proc directory 3306, and there's something here called stack. We're just going to do strings on the stack on the stack element here, and it's going to say, it's going to show us some things. This process is waiting, right? It's waiting to get its next command. Well, it says wait for more packets, right? Packet receive message, right? Again, Linux, open source, premier open source operating system. It wants to tell you what's going on. And the process here, it's waiting for its instructions. It's waiting in a loop, looking for packets to come in and decide what to do next. And it's just flat out telling you the libraries underneath I'm waiting for packets, right? So I know even if this thing were to say, I'm not sniffing traffic, the fact that it's calling these particular library calls, it is absolutely grabbing network traffic. Okay, third way to do it. The SS command has a really cool command line option called -0BP. What this says is list out all the processes that have a BPFDoor, that have a BPF filter operating on them. Now, you'll always get on the Linux system a couple processes that typically have some type of BPF filter in place, right? Usually it'll be like a WPA supplicant or a DHCP client or maybe systemd. There's usually one or two, but it's usually here what you see. This is the BPF bytecode that's running. It's usually a small amount. You know, it's basically doing stuff like give me all the UDP packets going to port 68 or something really simple. That's what it would translate to. But this third one here, and again, I can't capture the full width of this display, so just understand I truncated this a bit. It's a much larger amount of BPF bytecode because BPFDoor, it's not doing anything terribly sophisticated, the BPF, but it needs to do quite a few things in order to say, only grab this traffic going to this port that has this data in it and then do these other things on it. So it's a little bit more involved than a simple grab port 68 UDP or whatever else is going on. But in the case here, I see again this long BPF bytecode, and again it will show you, okay, the user of that is this sbin devd process PID 3306. So again, our suspicious process we're already investigating. The other ones up here would have shown like DH client or the WPA supplicant. It would have been kind of obvious what was going on. But this one here, again, a lot of bytecode. Interestingly enough, you could pass this bytecode here into ChatGPT and ask it to parse it back to a human readable like BPF filter, and it does kind of an okay job. It would kind of get you like 90% of the way there in terms of understanding what might be going on. So it might be something you can help doing. But the main point here is we see that this process is clearly using a more elaborate BPF filter, and the fact that it uses a BPF filter at all tells me again it is absolutely sniffing network traffic. Even if it says it's not, I know it is. Finally, the last thing we can do, never really, had to really get to this level, but I just wanted to show you a bonus way to detect people sniffing traffic, is we're just going to look at the file descriptors. So again, we're on the proc 3306, ls-al on FD, which is short for file descriptor. It shows you the open file descriptors the process has open. 0, 1, and 2 are standard in, standard out, standard error, pretty standard on Linux. And then it'll show you other files it might have open. In this case here, it has these sockets open, and in the brackets, the inode number. I'm going to take one of the inodes. I took 32057. I do grep 32057 procnet just to see what, what sockets are these listening on. And here on a procnet packet, this hex is the IP address. And then again, 32057. So here I can see again, this inode is clearly associated with someone grabbing packets or grabbing network traffic. So now we have 4 ways confirming that this process is absolutely grabbing network traffic. We don't know why it's grabbing it yet, but we definitely know that it's doing something suspicious. Now, the last thing this process did, which I talked on a little bit, is it protected itself against being easily found by using encrypted communications and covert channels in order to activate. In the case of the encrypted communications, because we already talked about the covert channel aspect of activation, it just used RC4. RC4 gets a lot of grief, but really I've always liked the algorithm because this is essentially it. This is the initialization and the encryption. They basically fit on the front and back of a cocktail napkin. It's small, fast, and secure enough for this particular application. Probably not the best choice, but good enough. The thing is, it's not going to match the encrypted protocol you expect to find on the port. And what I mean by that is if you saw this traffic going to 443, and let's say you had your act together enough that you were actually recording this traffic ahead of time, you would know it didn't do a TLS handshake and the traffic looks a little odd. It doesn't look like a web server traffic. It's maybe really low bandwidth going back and forth. I mean, it would look strange, but you'd really have to have your act together to see that type of thing. It'd be, you would do it. I think once you knew the backdoor is running, you could probably detect it, but unless you're watching all your systems in a very particular and unique way, it'd be pretty hard to find. So, overall, the encrypted communication is good enough for this application, I think. Work well enough. Could they have done something a little bit better, a little more elaborate? Probably. But again, evasive versus stealth, how complicated do you want to get to be? Do you want to risk breaking something? So I get why they use this. It was a reasonable choice. So all this, how does this all wrap together? Well, I mean, obviously, as I'm talking about BPFDoor, you could probably tell I actually thought it was a good piece of software. It was a good piece of malware. I've done a lot of red team vulnerability research and development through the years. And hey, man, I give them credit. It was really well done. I liked how they did it. And it kind of reminded me of this quote from Lord Percy in the American Revolutionary War. And essentially, he ran into trouble at Concord and Lexington against the American revolutionaries. And, you know, the British, the leaders in the British and the king, they're like, you know, these people are a bunch of farmers. You know, we're the British. We have the most powerful army and navy in the world. How could we possibly lose to these people? How could they give us such a hard time? And he said, they have amongst them those who know very well what they are about, right? And what he meant by this basically is, look, you should not underestimate these people because they know what they're doing. And that's kind of the way I think with BPFDoor, not just BPFDoor, but other Linux malware that we're starting to see more and more of now. There's a lot of it that's of a professional quality with people who definitely know what they are about, and they're after Linux networks in particular for very specific reasons. A lot of times it's critical infrastructure and other stuff. So, you know, you want to make sure that you take this stuff seriously. BPFDoor, in my opinion, was absolutely a professionally written and deployed and implemented piece of software used by people who knew what they were doing, and they have a very specific task that they want to accomplish. So how do I bundle all this up from professional malware versus the amateur stuff we typically see? Professional malware is going to be fast and reliable. Again, you don't want to crash a system because crashing systems gets people to look. It's going to be reliable and that it can run across many different versions of Linux without a bunch of hassle and complications. I mean, you know, the last thing you want to do is have to download a bunch of kernel headers because you're building a custom stealth rootkit to work in a box. I mean, it's completely infeasible. Second of all, this malware and other malware of the more advanced varieties, we're starting to see more clever security bypasses. They're not just coming in with with an axe, hacking thing to pieces. They're very much coming in with a scalpel, being very precise about what they're trying to do. And they're actually, in the case of BPFDoor, they actually used a valid security tool, the IP tables, in order to help itself succeed, which is a very clever use of a security bypass. And finally, the last thing is good malware doesn't try to outsmart itself. And yeah, I get it. You know, the elaborate hiding and stealth rootkit hijinks, they're cool from an academic perspective. I totally get it. But I have way more respect for evasive malware that doesn't outsmart itself. It's there to do a very simple job. It works all the time and it doesn't get anyone to notice it. That to me is really the sign of a really good piece of malware that doesn't go out there trying to outsmart itself. So my closing thoughts are, this is a very good piece of malware for Linux, obviously designed by people who knew what they were doing. There's a lot of other malware out there we're starting to see that's of similar ilk. I think we're seeing more sophistication on the Linux side of things. And a big problem on Linux is that it's not very well monitored. And this is something that our company is attempting to address with our agentless monitoring for Linux, is that if you're not looking at your Linux systems, I guarantee you someone else is. And those people have the tooling and the capabilities in order to make themselves hide on those systems for a very long time. I highly recommend to please keep a watch on your Linux systems, critical infrastructure, especially a lot of it's Linux. And if you're not watching those systems, you're going to find yourself very unpleasantly surprised one day, I promise you. So please take that to heart. And again, I'm Craig Rowland. I'm going to leave this QR code up here. You could follow me on Twitter. Also follow our company, Sandfly Security. We have a free version of our software that can, by the way, it easily found BPFDoor when it was released. Just by the way we worked. So we have free versions of that. We can help you out if you're worried about things like BPFDoor. And this QR code will take you to a technical analysis that we posted on BPFDoor last year that gets into the nuts and bolts of how it worked. So I hope you enjoyed this presentation. Thank you so much for watching. Please follow us on YouTube and Twitter and reach out if you have any questions or comments. I'd love to hear from you. Thanks again.